For today, we'll do a demonstration on one-way analysis of variance, particularly repeated measures, ANOVA. And we'll be doing this demonstration using SPSS. This is our dataset. Before that, let's go to our problem. So this is our problem. So a certain group of researchers examined the stereotypes we hold about attractive people. In the experiment, subjects looked at 4 types of photographs of persons all unknown to them. And there are 4 types of photographs, one having a physically attractive person, one of an average attractiveness, one of an attractive person, and one of a highly attractive person. Now, the subjects rated each photographed person according to how socially desirable the person is. Higher scores, of course, reflecting greater social desirability. So in this case, our model looks like this, wherein our attractiveness as a variable, and there are 4 levels. In this case, unattractive, average, attractive, and highly attractive. We'd like to know whether this attractiveness would have an impact or can influence or can predict the subject's perception of social desirability. So if that would be the case, therefore there should be a significant variance in the perceived social desirability ratings of the subjects when across different levels of attractiveness. So we use repeated measures ANOVA when we have a categorical variable, attractiveness, and there are 4 categories as I have mentioned. And when our independent variable, or a dependent variable rather, is a continuous variable. So this is our independent variable, which is categorical, and our continuous dependent variable. So this is our data set. Now the first thing that you'll notice here is that the way you enter data for repeated measures ANOVA is a bit different compared to between subjects or between groups ANOVA. So in between groups ANOVA, you actually have a variable and then the variations. Let's say, for example, if the variations of your IV is high or low are sort of coded as, let's say, for example, 0 or 1, and they are listed here in this column. But in the case of repeated measures ANOVA, these columns are actually not variables, but instead the levels of your independent variable. So our independent variable is attractiveness in the left, and the levels are the following: unattractive, average, attractive, and high attractive. And these values, on the other hand, refer to the ratings for social desirability. So to perform our analysis, let's click on Analyze. And then let's click on General Linear Model. Let's choose Repeated Measures. Let's wait for a while. My laptop is slow as usual. And then there will be a dialog box that would appear. So the first thing is we have to name our factor. So we only have one factor, and we have to identify the name. And the name of our factor for our IV is attractiveness. And we are being asked how many levels are there. There are 4. 1, 2, 3, 4. Let's click Add, and then let's define what are these 4 levels. Click Define. Okay. So what we do is we simply highlight all of these, and then transfer it here. So there you have the levels of our independent variable. Then before we run it, let's choose some options. Of course, we want to see the plots. Let's place attractiveness in our horizontal axis. Click add, continue, and then for post hoc, now post hoc makes pairwise comparisons, but we only use post hoc if we have a between subjects factor, but that would not be one-way ANOVA. That would be a split plot ANOVA. We have a between subjects factor and a within subjects factor, so no need for post hoc for the meantime. Click on options, and then attractiveness. Let's transfer it over to the other side, and then we want to compare main effects. So basically, this is the sort of the post hoc in the case of repeated measures ANOVA. Okay. And then you can choose LSD or Bonferroni. So let's choose Bonferroni this time. Okay. And then click on other options: descriptive statistics, estimates of effect size, and homogeneity tests. So that's basic. Now the significance level is at 0.05. If you want to be more strict, you can make that 0.01 or 0.001, but conventionally 0.05 is okay. Then let's click continue, and then let's click OK. So SPSS is now running the analysis. Might take some time. Don't worry, your computer did not hang. My laptop is still working on the analysis. And there, finally. Okay, so this is our output. So we have here a number of tables. So this basically tells us our levels, and then this is a bit of a preview of our descriptive statistics. So these where did that go? So these means represent the average social desirability ratings of the participants. By the way, I forgot to tell you that in the case of repeated measures ANOVA, there's only one group, and the same group are the ones who rated an attractive photo, average attractive photo, attractive and high attractive. Okay. So these are the means. What happened? So these are the means, the average social desirability ratings. These are the standard deviations. Multivariate tests, we don't want to look at that for the meantime. And then we have here the test of sphericity. So this basically indirectly tests whether or not the variances within the levels of our independent variable are roughly equal. Okay. So for the assumption to be satisfied, this should be not significant. So since the p-value is less than 0.05, so this means that there is a significant difference in the variances within the levels. So basically our assumption has been violated, and that would have some consequences in interpreting or in reading our ANOVA results. So this is the result of the ANOVA, and so the effect of so that these basically tell you the sources of effect, or what determines the social desirability ratings. So we have our factor, of course, attractiveness, and then we have the error factor. Okay. Now, first, let's assume that this is not significant, that the equality of variance was satisfied. Let's assume that this is not significant, that this is greater than 0.05. Then what we typically look at is this particular row. Sphericity assumed. So there is your degrees of freedom, your variance, your F ratio, and then your significance level. However, since so that's what you do if this is not significant. But since this is significant, so there has been a violation, there are some corrections in the analysis that we can choose. Now there are three, but maybe this would be enough. The greenhouse Geyser correction. So instead of reporting the original, then we can instead report the values in this greenhouse Geyser correction. So this is the sum of squares, the degrees of freedom. So sum of squares divided by degrees of freedom, we get our variance. And for the error, sum of squares, degrees of freedom, sum of squares divided by degrees of freedom, and then we get this variance. So this variance is the estimate of the variability across the variability in social desirability across the different levels of attractiveness, and this variance is the one which we expect by chance. So when you divide this mean square divided by this value, then we get our F ratio with the greenhouse Geyser correction. And noticeably there seemed to be not much of a difference, and the significance is and the p-value is significant, much less than 0.05. So that means that we are rejecting our null hypothesis, which says that our null states that attractiveness does not have an impact on social desirability. So when you reject that, this provides some evidence that attractiveness has some impact on social desirability, and that there is a significant difference in the variance in social desirability across the different levels of attractiveness. Okay. Now we also have here the partial eta squared, which is a measure of your effect size. And basically what this is telling us is that there is an estimated, or it is estimated that 74.2, so I converted this into percentage, 74.2% of the variability in social desirability can be predicted by the attractiveness of the person in the photograph. So that's a rather huge variance being accounted for by attractiveness. And then the next question would be, let's look at our plots first. Sorry. So this is our plot. So this is the average social desirability for those who were unattractive social desirability for those who are average attractive, social desirability rating for those who are attractive, and social desirability rating for those who are highly attractive. So there is a significant difference in the variance among these means. But the next question would be, what about if we compare? Where are the actual differences? Is there a difference between this and this, or this and this? And with that, we make a sort of a pairwise comparison. So using this particular table. So between 1 and 2, 1 is unattractive and attractive. There is no significant difference. So that means that these means are not significantly different. Between 1 and 3, p-value is less than alpha 0.05. There is a significant difference between this and this. And 1 and 4, there is a significant difference. And you can basically, and the rest of the table basically makes the other comparisons. 2 and 1 is basically 1 and 2. 2 and 3, significant. 2 and 4, significant. 3 and 1 is basically 1 and 3. 3 and 2 is basically 2 and 3. This is the new one. 3 and 4 is also significant. So there is also a significant difference. Sorry, let me double check that. 3 and 4, significant. So there's also a difference between this mean and this mean. So that's it. That's how you perform repeated measures ANOVA using SPSS. I hope it's helpful. And one last thing, how do we write that? How do we express that? So you can write F, then the degrees of freedom. So let's choose the degrees of freedom for the greenhouse gas correction, only because the test of sphericity was not was significant, and the assumption of equal variance was violated. So 1.111 and 16.660, 1.111 comma 16.660 equals, so the F ratio is 43.061, 43.061, comma, probability value equals 0.0001. Now I'm not particularly sure how do you express or how do you identify that this particular result is based on a greenhouse Kaiser correction. Still have to learn that. Alright, so that's it. Thank you for listening, and stay tuned for my next tutorials.